Okay, well, welcome back to College Physics 1. We're making some good progress in our course. Just as a reminder where we're at so far, we have been working through these various sections in mechanics. We talked about some of the units, the basic things that we'll be dealing with mass, with length, with time, with vectors, and introducing some of the methodological approaches with trigonometry, geometry, and algebra. We then talked about motion. We talked about motion in one dimension. We talked about two-dimensional motion. Now we're going to be getting into Newton's law of motion. So this is where it gets a little bit more complicated and interesting, where we're going to be starting to apply these principles and hopefully see how this can be quite useful when we're thinking of the world from a physics point of view. So in this figure, unless acted upon by external force, an object at rest will remain at rest, and an object in motion will continue to stay in motion. So in this case, the wall of the building did not exert a large enough external force on the moving train to stop it. And so that's the reason why we're seeing this. But now, unfortunately, it's in a situation where it's now at rest, and the building and the ground are providing enough opposite forces to keep it in that position as it speaks now, as it sits there in the picture. So let's do some reading questions review, then we'll get into the meat of the lecture. And so first of all, here is a question on an object moves with a constant velocity. Which of the following cannot be true of this object? A single force acts on the object. So with a constant velocity, which of the following can't be true? And so you typically have, if it's moving with a constant velocity, you have a variety of different things that are acting upon that object. And so, for example, gravity is going in the opposite direction, whatever. So those are some of the things that you can be thinking about for that question. For this question, an object accelerating when it experiences a non-zero net force, which of the following statement is always true? And so the answer for this one is the object's acceleration is in the same direction as the net force that acts upon it. And so if there's overall forces that are such that the negative and opposite forces is in the same, that you're going to see that there's movement in a certain direction. And here we're talking about acceleration, so that that force is maintaining itself at a constant level. So you will have acceleration, not just a steady state velocity. So what about for this one? A model rocket of mass m is fired upward from a launch pad with some initial speed v, a gravitational force exerted on the rocket. So what can we say about that? This is going to be true at all points in its motion. It's only if you got far enough from the Earth that you wouldn't have this gravitational force. But that's going to be gradually decreasing as the higher it goes up. But it's didn't specify what the intent of this launch pad was and how high you were trying to have it, if it's trying to go to the Mars or go into orbit or some other type of environment that could have been the case for that launch pad. So here's something in terms of a race car moving quickly down a track collides with a mosquito, which spatters on the car's windshield. You probably had that experience. Which objects experience a greater magnitude impact force? And so this is something that may not be intuitive, but they both experience the same force. The car had a lot more mass than the mosquito, but still there was the same impact that the mosquito had on the car as the car had on the mosquito. So that's something that hopefully you'll start to get a little bit more perspective as we continue on looking through this material. So a race car moving quickly around a track collides with a mosquito, which splatters on the car windshield. Okay, we just mentioned that. What object experienced a greater magnitude of acceleration? So this one was talking about impact force, and now we're talking about acceleration. So the car was going faster than the mosquito. So all of a sudden the mosquito is going to have a huge acceleration, that this force that was not there before is now making it go in a completely different direction. And its acceleration is greatly increased as a result of that impact. Fortunately, it probably didn't get a chance to experience that since it splat over the windshield. So when you sit in a chair, there is necessarily a reaction force to the gravitational force acting on your body. Which of the following best describes this reaction force? And so the answer is the force of gravity you exert on the earth. You are causing a force on the earth, just as like the earth is exerting a force on you. And if you're sitting still, then those are going to be in a balanced sense. So those are just some things that are attempting to try and have you get some review of the material, going through Newton's law, going through Newton's gravitational law. And these are the things that we'll be covering as we go through this chapter. So we want to turn our attention to what is called classical mechanics. Newton's laws are a lot of times called classical mechanics versus what you would get in modern physics with Einstein and what he developed with special relativity. So this describes a relationship between the motion of objects and the forces acting on them. If we aren't looking at objects comparable to the size of atoms or traveling closer to the speed of light, classical mechanics is an excellent description of nature. In this topic, we will look at Newton's 3 laws of motion and his law of gravity. These are considered to be among the greatest achievements of the human mind. It's kind of interesting to think that Sir Isaac Newton was able to come up with these. And so let's first start with thinking about forces. And so we'll be showing in a minute, a tennis player applies a constant force to the ball with his racket, accelerating and directing the ball towards the open court. So I'm sorry that the figure is not showing up here, but anyway, you can imagine a force as a push or a pull on some objects. For example, when a tennis ball is hit with a racket, the player can hit the ball in different speeds and direct it into different parts of the opponent's court. The applied force has magnitude and direction, so force is a vector quantity, just like velocity and acceleration. So here's another example of force applied to various objects. In each case, a force acts on the object surrounded by a dashed line. Sometimes in the environment external to the boxed area exert the force. So you can imagine pulling on a spring, the spring stretches. If you pull hard enough on a wagon, the wagon eventually moves. When you kick a football, it deforms briefly and then is set in motion. So these are just some examples of the kinds of forces that you can be doing. And this might be like, say you're in the weight room, you're seeing something kind of like that with some of the equipment, or maybe this is just resistance training of a certain type. Here, maybe you're just using it, you're one of your relatives or one of your kids in the future, you're taking them out. Or if you're into sports, the engaging with a football, soccer ball, volleyball, whatever it might be. So these are all examples of exerting forces. Now we're getting into another area and this is the classes of forces that don't involve any direct physical contact. Early scientists, including Newton, were uneasy with the concept of forces that act between two disconnected objects. Even so, Newton used the action at a distance concept in his law of gravity, which says that a mass at one location, such as the sun, affects the motion of a distant object, such as the earth, even though the two are not in evident physical content. Michael Faraday introduced the concept of field to help conceptualize these actions at a distance phenomena. The corresponding forces are called field forces according to the approach an object of a mass m, such as the sun, creates an invisible influences that stretches throughout space. A second object of mass m, such as the earth, interacts with this field of the sun, not directly with the sun itself. So the forces of gravitational attraction between the two objects illustrate that the left-hand figure is an example of a field force. The force of gravity keeps an object bound to Earth and also gives rise to what we call weight of those objects. And so here's just some examples of how those might work in different types of things that we just mentioned. So there's actually several different types of forces. And so these are known as the fundamental forces in nature that are all field forces. These include in order of decreasing strength versus the strong nuclear force between subatomic particles. The second is the electromagnetic forces between electric charges. Third is a weak nuclear force, which arises in certain radioactive decay processes. And finally, the gravitational force between objects. The strong force keeps the nucleus of the atom from flying apart due to the repulsive electrical force of the protons. The weak force is involved in most radioactive processes and is important in the nuclear reaction that generates the sun's energy output. Strong and weak forces operate only on the nuclear scale with a very short range on the order of 1 to say 10. Anyway, it's a very short order that's at the atomic domain. Outside this range, they have no influence. Classical physics deals only with the gravitational electromagnetic forces, which have infinite range. And so this is we dealing with the electromagnetic forces and the gravitational forces. But we wanted to mention in context that you see those other forces, and we'll be coming back to those in later chapters. So we want to be starting to spend some time with Newton's laws, and there's various ways that you can be thinking about them. And so here's one. So this is the first law of motion. A book at motion at an interval velocity of v on a surface with friction, because there is a friction force acting on the horizontally, the book slows down to rest. So you engage with the force, but there's a force of friction, and over time, as it's going across the table, and probably you would want this to happen, it doesn't fall off the table. So you can think about this book on the table. If we leave the book alone, it remains at rest. Now imagine pushing the book, with a horizontal force great enough to overcome the force of friction between the book and the table, setting the book in motion. Because the magnitude of the applied force exceeds the magnitude of the friction force, the book accelerates, as illustrated in the figure. When the applied force is withdrawn, friction slows down, and the book eventually stops. So you've applied a force. It starts out with a velocity. That velocity decreases. There's an acceleration. There's a constant acceleration in the opposite direction due to the friction. And so that's what we're seeing there. So here we see an example of a book moves at velocity v on a frictionless surface. In the absence of a net force, the book keeps moving at velocity v. So maybe if you've ever played air hockey, it gets you into the situation where the coefficient of friction is much less. And so we're trying to give an example of how that would look. So if you apply a force, it doesn't have any repelling force, and it's going to continue to go in motion. So now we can imagine pushing the book across a smooth wax floor. That would be maybe another way of looking at this. The book again comes to rest once the force is no longer applied, but not as quickly as before. Finally, if the book is moving on a horizontal frictionless surface, as shown in this figure, it continues to move in a straight line with constant velocity until it hits a wall or some other obstruction. Newton's first law of motion in an object moving with a velocity that is constant in magnitude and direction unless a non-zero net force acts on it. So it will, what's in motion stays in motion, and what's at rest stays in rest. So before Newton's time, it was generally assumed that the natural state of matter was a state of rest. Galileo devised thought experiments such as an object moving on a frictionless surface, as was on the previous slide, and concluded that it's not the nature of an object to stop once it's set in motion, but rather continue its original state of motion. This idea was later formalized with Newton's first law of motion, that an object moves with a velocity that is constant in magnitude and in direction unless a non-zero force acts upon it. So maybe, like I said, what is in motion stays in motion, and what's at rest stays at rest. The net force on an object is defined as a vector sum of all external forces exerted on the object. External forces come from the object's environment. If an object's velocity isn't changing in either magnitude or direction, then its acceleration and the net force acting on it must both be zero. Internal forces, on the other hand, originate within the object itself and can't change the object's velocity. Although we will see in a later topic that they can change an object's rate of rotation, because they don't influence an object's velocity, internal forces aren't included in Newton's first law. It's not really possible to push yourself up by your own bootstraps. So that's we'll start with that. So let's give a little bit of thought in terms of what mass and inertia is. And so inertia is the tendency of an object continue in its original state of motion. Mass is a measure of the object's resistance to change in its motion due to force. So imagine hitting a golf ball off a tee with a driver. If you're a good golfer, the ball will sail a couple of 100 yards down the fairway. Now imagine teeing off a bowling ball and striking it with the same club. Not really something I would be recommended. Your club would probably break. You might sprain your wrist, and the bowling ball at best would fall off the tee, taking half a roll and come to rest. For this, we can conclude that although both balls resist change in their state of motion, the bowling ball offers much more effective resistance. So the tendency of an object to continue in its original state of motion is called inertia. So you have to overcome that inertia if you want to make it move. So a measure of the object's resistance to change is its motion due to a force is called mass. And so that's related to weight. And we've had a little bit of introduction to that. The kind of mass is often called inertial mass because it's associated with inertia. The greater the mass of a body, the less it accelerates under the action of an applied force. The SI units of mass is the kilogram. Mass is a scalar quantity, so it obeys the rules of ordinary arithmetic. So let's look at a mechanical arrangement for an automobile seat belt. And so we're seeing how it deploys, it tightens up on the individual using it. So there's a variety of different things that are used when we conceive that. So we can use the concept of inertia to explain the operation of the type of seatbelt mechanism. So the purpose of the seatbelt is to hold the passenger firmly in place relative to the car to prevent serious injury in the event of an accident. So if we take a look at the figure, under normal conditions, the ratchet turns freely to allow the harness to wind on or unwind from the pulley on as the passenger moves. In an accident, the car undergoes a large acceleration and rapidly comes to rest. Because of its inertia, the large block under the seat continues to slide forward along the tracks. The pin connecting between the block and the rod causes the rod to pivot about its center and engage the ratcheted wheel. At this point, the ratchet wheel locks in place and the harness no longer unwinds, thus protecting the passenger. And so that's the whole point, is to keep them from hitting the dashboard or the windshield or something like that. So we talked about Newton's first law. Well, now let's talk about Newton's second law. And so we see force mass and acceleration being listed as the things that we're going to be talking about here. F equals ma is an important concept that you're going to be getting as a result of this. And so Newton's first law explained what happened to an object that had no net force acting on it. The object either remained at rest or continued moving in a straight line with a constant speed. Newton's second law answers the question of what happens to an object that does not have a net force acting upon it. Imagine pushing a block of ice across a frictionless horizontal surface. When you exert some horizontal force on the block, it moves with an acceleration of, say, 2 meters per second squared. If you apply a force twice as large, acceleration is double at 4 meters per second squared. Pushing 3 times as hard triples the acceleration, and so forth. From observations like these, we conclude that the acceleration of an object is directly proportional to the net force acting upon it. And so here is just where we see that if you're varying the force, and so the force is inversely proportional to the mass, and we're starting to get to this equation that's quite helpful. So with the second law of motion, for the block of mass m, the net force, the summation of F acting on the block equals the mass m times the acceleration vector a. And so here we're starting to get into, well, what if we wanted to be having a coordinate system and an X, Y, and Z coordinate system? So far, we've just talked about 1 or 2 coordinate systems, and now we're bringing into this idea of 3. So the figure illustrates the relationship between the mass, acceleration, and net force. The second law is a vector equations. So it has the 3 components that are shown. When there is no net force on an object, and acceleration is 0, which means that the velocity is constant. Well, what about units of force and mass? And so the thing that maybe might not be as familiar to you as these SI units, but in all kinds of science, this is the thing that you use. And so we have terms for mass, for acceleration and force. Kilogram is the units for that, or slugs in the US customary type of things. Acceleration is meters per second squared, and force is in kilogram meters per second squared. And for US, that would be slugs per foot over second squared. And so 1 Newton is 1 kilogram meters per second squared, and in terms of US units, it's 0.225 pounds, just to give you some perspective. So just some questions for us to think about. True or false, an object can move even when no force is acting upon it. So the answer is true if the resulting force of an object is 0, because no forces are present, or the vector sum of is present. The object can still move with constant velocity. What is at rest stays at rest, and what is moving continues to move. And so maybe that's a perspective that you might want to be thinking about. If an object isn't moving, no external forces acted on it. It's false. An object that remains at rest has 0 acceleration, although any number of external forces could be acting on it, providing that the vector sum of these forces is 0. Something is sitting on the table. The force of gravity is counteracted by the force that the table is keeping it on top of the table. If a single force acts on an object, the object accelerates. This is true. When a single force acts, the resulting force cannot be 0, and the object must accelerate. Okay. If an object accelerates, at least one force is acting upon it. That's true. When an object accelerates, a set containing one or more forces with a non-zero resultant must be acting upon it. If an object isn't accelerating, no external forces are acting upon it. False. If the resulting forces on an object is 0, the object can still be moving with constant velocity. objects either stay at rest or they continue to be moving. Just because it doesn't have any force acting upon it, it could already have a force that has acted upon it. If the net forces acting on an object is in the positive x direction, the object moves only in the positive x direction. Not necessarily. If the net force is in the positive x direction, the acceleration will be in the positive x direction. However, the velocity of an object does not have to be in the same direction as the acceleration. You can be considering the motion of a projectile, which we talked about last time with a two-dimensional scenario, X and Y. And let's now just be thinking a little bit more about Newton's law of gravity. And so we have the gravitational forces between two particles is attractive. The gravitational force is a mutual force of the attraction between any two objects in the universe. Even though the gravitational force can be very strong between two very large objects, it is the weakest of the fundamental forces. Maybe something for you to remember. Let's see just how weak gravity is. Imagine rubbing a balloon in your hair, which gives the balloon a tiny electrical charge. Because the electrical force of the balloon will stick to the wall and resist the gravitational pull of the earth. So that's just an example of giving you some idea of the size of the force. Newton's law of universal gravitational states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to its square of the distance between them. We're attracted by the sun. We maintain an orbit around the sun here on Earth. The moon is in orbit around the Earth. And so those are just maybe some examples of we're seeing those forces, that there's different coordinate systems and the aggregation of things that we need to be mindful of. If particles have mass m1 and m2 and are separated by a distance r, as shown in the figure, the magnitude of the gravitational force is given here. There's a universal gravitational constant called g, and we'll consider that in a later topic. And so G is this constant, and here is a value that is assigned to that, and here is the Newton's law of gravitation that is specified there. Something worthwhile keeping in your mind. Okay, the magnitude of the gravitational force acting on an object mass m is called the weight W of the object, which is given by the equation shown where G is the acceleration of gravity. And so this is how we would be figuring out that G relative to the gravitational force on the Earth, on the moon, whatever. And so this is what we experience. We can write an alternative definition of the weight of an object with mass m using Newton's law of gravitation, where ME is the mass of the Earth and R is the distance from the object to the Earth's center. If the object is at rest on Earth's surface, then R is equal to the Earth's radius. Because R squared is the denominator, we can see that the weight decreases with increasing R. So the weight of an object on a mountaintop is less than the weight of an object at sea level. So this is how we can start to figure that out. We can write G, the gravitational acceleration is shown, and G is 9.8 meters per second squared. And just as a reminder, that's one of those values that might be worth keeping in mind. So here we have a picture of somebody on the moon. And so the life support unit strapped to the back of an astronaut weighs, say, 300 pounds on Earth and has a mass of 136 kilograms, put it in SI units. During his training, a 50-pound mock-up with a mass of 23 kilograms was used, although the mock-up had the same weight as the actual unit would have on the moon. The smaller mass meant it also had a lower inertia. The weight of the unit is caused by the acceleration of the local gravity field, but the astronaut must also accelerate anything he's carrying in order to move it around. Consequently, the actual unit used on the moon with the same weight but greater inertia was harder for the astronaut to handle than the mock-up on Earth. At least trying to do some kind of training to give them some preparation for that. Unlike mass, weight is not an inherent property of an object because it can take different values depending on the value of g in a given location. If an object has a mass of 70 kilograms, for example, then its weight at a location where g is 9.8 meters per second squared, m times g is 686 newtons. And in a high altitude balloon where g might be 9.76 meters per second squared, the object weight would be 683 newtons. And so we're seeing a little bit of difference depending on where you are, either on the surface of the Earth, up in a mountain, or what have you. So the value of g also varies slightly due to the density of mass in a given location. In this course and in our textbook, unless stated otherwise, the value of g will be understood to be 9.8 meters per second squared, its value near the surface of the Earth. So we have some questions here to do some review. I'm just going to run through these fairly quickly, since there are quite a lot of these. But you can always review these at your leisure. So, which has the greatest value, a Newton of gold, 1 on Earth, or a Newton of gold, 1 on the moon? And so the Newton of gold on the moon. So that would take a lot more mass because the weight on the moon is much less. So true or false? No force of gravity acts on an astronaut in orbiting space. False. So there's all kinds of different gravitational forces when a astronaut is in an orbiting space station. They're just not as strong as the component from Earth. There's a component from the moon, and other things. The Earth is not completely flat, so the pull of the Earth, depending if you're over Mount Everest or down or above an ocean, would be different. So at 3 Earth radii from the center of the Earth, the acceleration of the gravity is 1/9 its surface value. True. So you're 3 times away, so there's a factor of 3. So that squared is 9, and so that's what you're seeing, it's 1/9. True or false? If 2 identical planets, each with surface gravity g and volume v, coalesce into one planet with a volume 2v and a surface gravity of the new planet is 2g. The answer is false. The acceleration of the gravity on the mass of the surface planet m with volume v is g. We have the general equation for gravity. If the mass and volume are doubled, the radius becomes it's not just 2r, it's actually something larger, and the surface gravity is not quite what they were specifying here. So those are some of the things to keep in mind. If you just actually put these into Newton's equation for gravity, you can get some clarification on that. True or false? 1 kilogram of gold would have greater value on Earth than it would be on the moon. False. So the weight of an object, its mass, is independent of the local acceleration of gravity. Thus, 1 kilogram of gold contains the same amount of gold on the moon as it does on the Earth. We're talking about mass and versus weight. Weight is dependent on the gravity. So with Newton's third law, the force exerted by the hammer on the nail is equal to the magnitude in opposite direction to the force exerted by the nail on the hammer. So we can imagine driving a nail into a block of wood as shown in the figure to accelerate the nail and drive it into the block. The hammer must exert a net force on the nail. Part of Newton's genius was that he recognized that a single isolated force couldn't exist, but the forces in nature always existed in pairs. According to Newton, as the nail is driven into the block by the force exerted by the hammer is slowed down and stopped by the force exerted by the nail. So here in this picture, the force F12 exerted by object 1 on object 2 is equal in magnitude and opposite in the direction to the force F21 exerted by the object 2 on object 1. So that's what we're seeing. So Newton's describes such paired forces with his third law. If object 1 and object 2 interact, the force F1 exerted by object 1 and object 2 is equal in magnitude but opposite in the direction to the force F21 exerted by the object 2 on 1. This law is illustrated by the figure and states that a single isolated force can exist. The force F12 exerted by object 1 and object 2 is sometimes called the action force, and the object F21 exerted by object 2 on object 1 is called the reaction force. In reality, either force can be labeled the action or reaction force. The action force is equal in magnitude to the reaction force and opposite in direction. In all cases, the action and reaction forces act on different objects. So if we think of a freely falling projectile, the force acting on it is the force of gravity exerted by the Earth on the projectile, F sub g, and the magnitude of the force on its weight is m times g. The reaction to the force F sub g is the gravitational force exerted by the projectile on the Earth. The reaction force accelerates the Earth towards the projectile the same way that the action force accelerates the projectile towards Earth. But remember that the Earth is huge. Its acceleration due to this reaction force is negligibly small. So when walking, for example, we exert a frictional force against the ground. The reaction force of the ground against our foot propels us forward. In the same way that the tires on a bicycle exert a frictional force against the ground, and the reaction of the ground pushes the bike forward. So you can be thinking of a monitor on a table. The forces acting on the monitor are the normal forces N exerted by the table, and the forces of gravity. And so if it's staying still, we see that these gravitational forces are the same. So I think that may be enough to make that point, that we're seeing that these two similar but opposite forces enlisted in these equations. So the forces N and N prime both have the same magnitude as Fg. Note that the forces acting on the monitor are Fg and N, as shown in the figure at the right. The two reaction forces, Fg prime and N prime, are exerted by the monitor on the objects other than the monitor. Remember that the two forces in an action-reaction pair always act on two different objects. Because the monitor is not accelerating in any direction, Newton's second law gives us the relationship shown. Okay, a couple more questions here. A small sports car collides head-on with a massive truck. Which vehicle experiences the greatest impact force? And the answer is neither. The force is the same on both. So something to keep in mind. So, but here's another thing, which has the greater acceleration? The car. Newton's second law states that acceleration is inversely proportional to the mass and the force is constant. Thus, the lower mass vehicle, the car, will experience a greater acceleration. Okay, we'll talk about a couple of cases now. And so this is the normal face on a level surface. And so that's what we're seeing. And in this first case, and then the second case is a free body diagram here. So the figure on the left shows a block at rest on a flat surface. The two forces acting on the block are the normal forces acting upward and the gravity force directed downward. The figure on the right is called the free body diagram for the block when only the force acting on the blocks are shown Free body diagrams include only the forces acting directly on the object in question. So any force that you threw this object, and of course you have gravity going in the opposite direction. And we have the accompanying position equations that are associated with them. And we can see that they would be net for this case. And so that's how that's coming out. So here's another case. So we have a normal force on a level surface with an applied force. And so here we're starting to show an angle. It's not just directly flat like pushing a book across the table. So we have an applied force on a positive angle. We have a free body diagram. So whatever you can be thinking of us hitting a baseball with a bat and it goes at a certain direction. And so the figure, so the thing here is we're having this direction that this force is being applied. So there's going to be an X component, there's going to be a Y component, and the things that we previously covered will become applicable here as we get into this in more detail. So let's apply the second law of motion to the Y direction. And this second equation can easily be solved for the normal force N. Notice that if the angle is positive, then the sign of the angle is positive, and the X component of the applied force supports some of the weight, reducing the normal force. This is clear when we separate out the Y components, as in the figure on the far right. The sum of the applied forces and the Y component of the applied force is equal to the magnitude of the weight. So here we're just trying to be showing the Y components here. If the angle is negative, then the sign of the angle is also negative, making a positive contribution to the normal force as illustrated in this diagram. The normal force must be larger, and in this case, its magnitude is equal to the sum of the weights and the Y component of the applied force. So what about an object under acceleration? So the figure shows a block on a flat surface that is under acceleration. For example, in an elevator, the two forces acting on the block are the normal forces directed upward and the gravity forces directed downward. And acceleration upward increases the magnitude of the normal force because the normal force must not only compensate for gravity, but also provide the acceleration. The Y component of the second law of motion yields the equation shown. So just we're seeing how we can be applying F equals ma in a couple various situations. Now let's look at things in a slope. So you have a block on a slope, and so what are the forces here? We can be looking at those various elements using trigonometry to break out the sine and cosine for the X and the Y components here. And so that's what we're trying to do. So this is a problem that you'll see in a variety of situations where an object resting on a surface tilted at some constant angle. If you rotate your coordinate system so that it's tilted in the same direction, this really simplifies the mathematics of these types of problems. Of course, any orientation of the coordinate system will give you the same answer because changing our coordinate system doesn't alter the physics, but simplifying the math is a nice idea. So that's something that I would definitely want to have you folks remember, is there's no reason to make a problem harder than it needs to be. So you can come up with a new coordinate system, Y prime and X prime, and then start to make your math a little bit more straightforward. So what about the normal force and atmospheric pressure? So we've seen the normal force acting on the object, for example, a block on a level surface opposes the gravity forces pulling the block towards the center of the earth. Technically, the normal force also opposes the downward pressure of the atmosphere on the top of the block. Because of microscopic imperfections, air filtration between even a very smooth object resting on a relatively smooth surface effectively cancels out the downward pressure with an equal upward pressure. When air can be excluded from beneath an object, then atmospheric pressure acts only downward and the object is held very firmly in place. This is the suction cup effect that allows suction cup darts to stick to windows. It works better when the cup are slightly damp, et cetera, et cetera. So we're just starting to be thinking about when you actually drop an object with an atmosphere, it doesn't accelerate at 9.8 meters per second squared because of the impact of the atmosphere. So let's talk about the force of friction, kinetic friction. And so friction is a constant force from the microscopic interactions between a body and its environment. Air friction affects vehicles from cars to rockets. Fluid friction affects the motion of ships on the passage of fluid or the passage of fluid in pipes. But don't get the wrong idea. Friction is not always something that impedes motion. Without friction, we wouldn't be able to walk or pick up and hold objects. Friction is also caused when an object is in contact with a surface. So microscopically, tiny protrusions on the interaction surface interlocked and soften and break or bend when force is applied. Kinetic friction is friction that arises during motion. It depends on the materials that the surface are made of and how smoothly they are and how firmly they are in contact. The normal forces is a measure of that firmness of contact. And so it makes sense that the greater the normal force, the larger the kinetic friction force. In general, we model the interaction between two surfaces as being proportional to the normal force. The magnitude of the kinetic friction force, F sub k, acting object moving on a surface is given by the equation here, where n is the normal force acting on the object and mu sub k is called the coefficient of kinetic friction between the object and the surface. The force F sub k acting in the direction opposite to that direction of motion. So calculating the kinetic force is easy. First find the normal force and then multiply it by the coefficient mu sub k. And here is a picture. Here's a list of the coefficient of frictions for various surfaces. And so that the coefficient depends on the object and the surface and determined experimentally. In reality, surface variations we can't see can affect the value of the coefficient as the velocity of the object. And in any case, these coefficients are useful, but we should think of them as averages over time and approximations. For our purposes, we'll assume a coefficient of friction is always constant for a given surface and object. The table shows representation values for the coefficients of kinetic and static friction. We'll look at static friction in a little while. So static friction is what does it take to get moving, and the kinetic friction is what does it take to have it maintain in motion. So both of those are important factors that we want to be aware of. So here we're looking some more at Newton's third law with kinetic friction acting upon an object's direction of motion. So the diagram illustrates the effects of kinetic friction upon a block. And so now we have another force that we have to contend with that we're starting to have a little bit more detailed understanding. Then we can write the exponent of the second law of motion and include this kinetic impact here, as we're showing there. The angle of an applied force is critical for us to determine the resultant acceleration of the block. As the angle increases from zero, the part of the applied force acting in the x direction decreases, as do the normal and kinetic friction forces. So let's talk about the static friction. So you can think of us when you're trying to move a trash can. So when a horizontal force is exerted against the trash can, it typically doesn't move unless the force exceeds some critical value as depicted in the figure. The critical value is the maximum static friction force. The actual static friction force is always less than or equal to the maximum as the the kinetic friction force. The static friction forces rises from microscopic interactions between the object and the surface it rests upon. So here's a graph of the magnitude of the friction force versus applied force. And so the graph illustrates how static friction works. As the applied force gradually increases, so does the static friction force acting in the opposite direction. When the applied force exceeds a maximum static friction force, the object begins to move, and kinetic friction takes over. In general, the kinetic friction coefficient is less than the static friction coefficient. The magnitude of the static friction force acting on an object at rest satisfies the inequality shown, where n is the normal force and mu sub s is the coefficient of the maximum static friction force between the object and the surface. The force F sub s acts in the direction opposite that of the impending motion, which you can think of as the motion that results if static friction were not sufficient to prevent it. And so here is looking at a couple cases where we're applying forces in increasing fashions. So the static friction, as in A and B, however, the refrigerator doesn't move. When the applied force surpasses the maximum static friction, the refrigerator begins to move. Unlike the kinetic friction force, the static friction force takes on any value between 0 and its maximum value, depending on the magnitude of the applied force. So, so here's a question for us to be quickly thinking about this. We'll just have a few, and then we'll just briefly go over these. If you press a book flat against a vertical wall with your hand, in what direction is a friction force exerted by the wall or the book? And the answer is it's out of the wall. Friction forces are always parallel to the surface in contact. That's the rationale. So a crate is sitting in the center of a flatbed truck. If the truck accelerates to the east, the crate moves with it, not sliding on the bed or of the truck. In what direction is the friction force exerted the bed of the truck on the crate? And it's to the east, in the same direction that the truck is accelerating. Suppose your friend is sitting on a sled and asks you to move her across a flat horizontal field. You have a choice of A, pushing her from beyond by applying a force downward on her shoulder at 30 degrees below the horizon figure, or B, attaching a rope to the front of the sled and pulling with a force 30 degrees above the horizon. Which option would be easier? And the answer would be situation B. It's easier to attach a rope and pull. In this case, there is a component of your applied force that is upward. This reduces the normal force between the sled and the snow. In turn, that reduces the friction forces between the sled and the snow, make it easier to move. So maybe those are some things that might be worthwhile thinking about if you ever have a situation that would fall into that kind of a category. So a strong man pulls a car via a tension rope, but must lean forward to prevent an equal and opposite tension force from causing him to topple over backwards. So we look at the figure of a man pulling this car. There's a tension force in the rope, which acts along the direction of the rope and exerts a force on the car and the man. If we neglect the mass of the rope, the tension is the same all along it. The tension force on the car, T sub C, has the same magnitude as the tension force on the man, T sub M. You can think of the tension force as a force that would be read on the spring scale if we were spliced into the cable. Tension forces are due to microscopic electromagnetic interactions that resist the separation of the long, thin string of matter when a force is applied to it. The string becomes taut, and through it, the force can then be transmitted to the object that the cable is attached to. So what about the tension in the string supporting a block weight? So you're hanging a chandelier or whatever it is that you might be thinking about here. So this shows an object is dangling at the vertical end of a vertical string. The object is in equilibrium, so the acceleration is 0. The y component of the second law gives an expression of the tension in the string. As you can see, the tension force is equal to the supporting weight. What about vertical tension forces on an accelerating object? So you can be thinking of in the figure, a string is attached to an object and put under tension so that it accelerates the object upward. The tension force must support the weight and in addition provide the acceleration. The correct expression can be derived from the y component of the second law given in the equation shown below. This can be rearranged algebraically to get the result shown. Accelerating upward increases the tension, whereas accelerating downward decreases the tension. So, so consider tension force at symmetric angles. And so, and in this case shown, the figure, two tensions act on one object symmetrically. For this to work, the points of attachment must be chosen carefully, in which case the tensions will be equal. So we can apply Newton's second law in the y direction. The components of each tension is given by t cosine of theta, and the weights act downward. Since the object is not moving, the acceleration is 0. We can solve for the tension t, as shown in the equation. Whether the expression involves a sine or a cosine depends on what angles are given in the problem. So something to think in mind. So you're suspending an object with 2 points in a ceiling, for example. That might be one way that you could be thinking about that. What about two tensions at non-equal angles? So maybe it's tied to the wall and tied to the ceiling. Sometimes you'll see situations where the tensions are from non-equal angles, as example shown here. In these two cases, you need to write two equations with two unknowns for the two tensions, T1 and T2. Notice that in this case, the given angle of 30 degrees is respect to the vertical so that the adjacent side of the triangle forms by the vector T2 corresponds to the y direction, which is requires a cosine function. With a sub y equals 0, the y component of the second law yields the equation here, which can easily be solved for the tension T sub 2. Again, the given angle 30 degrees is with respect to the vertical, so the opposite side of the triangle forms the vector T2 corresponding to the x direction, requiring a sine function. When a sub x equals 0, the x component of the second law can be solved for the tension T1. So the basic procedure is using the two components of the second law, write two equations and solve for two unknowns. So it's a little bit more complicated, but it's still following the same general principle that we've already talked about. So here's an example where we have a rope. We are ready to apply Newton's law to objects under the influence of constant equal forces. We will assume that the objects behave as particles, so we don't need to consider the possibility of rotational motion. We also neglect any frictional effects in the masses of the ropes or strings involved. With these approximations, the magnitude of the tension exerted along the rope is the same at all points in the rope. So when we apply Newton's law to an object, we are interested only in those forces that act on the object. Look again at the figure of the monitor. The only external force acting on the monitor are N and F sub G. The reactions to these forces, N prime and FG prime, act on the table and on Earth, respectively, and don't appear in Newton's second law applied to the monitor. So finishing up with Newton's third law, let's consider a crate being pulled to the right on a frictionless horizontal surface as the figure shows. Suppose you wish to find the acceleration of the crate and the force the surface exerts on it. The horizontal force exerts on the crate acts through the rope. Force that the rope exerts on the crate is denoted by T because its tension force. The magnitude of T is equal to the tension on the rope. A dashed circle is drawn around the crate to emphasize the importance of the isolating the crate from its surrounding. Because we are uninterested, we are interested only in the motion of the crate, we must be able to identify all forces acting upon it. The free body diagram illustrates these forces. The free body diagram for the crate also includes a force of gravity F sub g exerted by Earth and the normal force and exerted by the floor. The construction of the correct free body diagram is an essential step in applying Newton's law. An incorrect diagram will most likely lead to incorrect answers. The reactions to these forces, the forces exerted by the rope on the hand, doing the pulling, the force exerted by the crate on the earth and the force exerted by the crate on the floor aren't included in the free body diagram because they act on other objects and not on the crate. This means that they don't directly influence the crate's motion. Only forces acting directly on the crate are included. Now let's apply Newton's second law to the crate, first by choosing an appropriate coordinate system. In this case, it's convenient to use the one shown in the figure with the x-axis and the y-axis vertical. The x-axis horizontal and the y-axis vertical. We can apply Newton's second law in the x direction, y direction, or both, depending on what we're asked to find in the problem. The results are shown here. From these equations, we find that the acceleration in the x direction is constant, t over m, and that the normal forces given by n equals to mg. Because the acceleration is constant, we can use the equations of kinematics as needed. So here is a problem-solving strategy for Newton's second law, and these summary slides are actually quite useful. And I think you're starting to notice some similarities. That the first, you want to be reading the problem. You want to draw a picture of the system, identifying the objects of primary interest, and indicate the forces. Label each forces in the picture in a way that will bring to mind what physical quantity the label stands for. So say for T for tension. We want to then draw a free body diagram of the object of interest based on the labeled pictures. If additional objects are involved, draw separate free body diagrams for them. And you want to choosing a convenient coordinate system for each object. And you want to apply Newton's second law. The x and y components of Newton's second law should be taken from the vector equation and written individually. This usually results in two equations and two unknowns. And then finally solve for the desired unknown quantities and substitute the numbers. In the special case of equilibrium, the foregoing process is simplified because the acceleration is 0. So we'll talk about objects in equilibrium here. So objects that are neither at rest or moving with constant velocity are said to be in equilibrium. Because A equals 0, this equation shows that the vector sum of all the forces, that the net force acting on the objects in equilibrium is 0. We can write Newton's second law for x and y components as we're showing here. We won't consider three-dimensional problems in this course, but we can extend our components to a third-dimensional problem by adding the third equation for the z component. So just a few questions here, and I'll just go over this quickly. So consider the two situations shown in the figure in which there is no acceleration. In both cases, the men pull with a force of magnitude F. How does the reading on the scale in figure I relate to the reading on the scale in figure 2? So the scales in both situations give identical readings. And so this may not be intuitive, but maybe you've ever seen somebody that they play tennis with somebody, and then there's also places where you can see that they hit the ball against the wall, and you can get the same kind of a scenario by thinking about that if you like. The scale records the tension in the rope attached to its right end. The section of rope in the man's hands has 0 acceleration, and hence the 0 net force acting on it. This means that the tension in the rope pulling to the left on the section must equal the force F on the man exerting towards the right of it. The scale reading in this case will then be F. In case 2, the person on the left can be modeled as simply holding the rope tightly while the person on the right pulls. Thus, the person on the left is doing the same thing as the wall does in case 1. The resultant scale readings is the same when either there is a wall or a person holding the left side of the scale. For the women pulling forward on a toboggan in the figure below, the magnitude of the normal forces exerted by the ground of the toboggan is, and the answer is less than the total weight, because you're actually, there's a component going up, and so that helps to reduce the coefficient of friction that you're having to overcome. And so that actually maybe not as intuitive until you think about it, actually is helping you out. So let's talk about the two body problem, the systems approach. You can also apply Newton's second law of motion to systems of objects. If two bodies are connected by an inextensible string, so that the bodies have a common acceleration, it's possible to use the system approach, which treats the bodies as a single object. The second law of motion for the system approach is shown here, where F sub external, ext, are forces external to the system. Internal forces, for example, a tension force holding the system together, do not appear. Internal forces must be found by applying the second law to individual bodies in the system. The system approach naturally can be extended to 3 or more bodies. So we have a bunch of questions here, and I'm just going to quickly go through these. And so you can look at them at your leisure, but I'm not going to spend a lot of time on either one of these. So a baseball is struck by a bat. While the bat is in the air, what object exerts the force? And the answer is the earth and the air. 3 bodies are stacked as shown below. How many forces are acting on the bottom block? And the possible answers are 3 and 4. So you can be thinking about that. A block of mass M is on a rough surface with a spring attached and extended. As the block moves on the incline a small distance, how many forces are exerted on the mass? And the possible answers are 4, 5, 6, 7, and 8. And so there's all kinds of interesting forces that you can be thinking about, depending on how complex you want to be getting into the answer. The monkey hangs on a rope. With what forces act on the monkey? So you want to ignore forces due to the air. Possible answer are number 1 and number 2. So a thin wire is stretched horizontally between 2 walls. If a weight W is hung on the wire, what is true about the tension T in the wire? The answer is T is greater than W. So we want to consider the following: 100 grams of steam on the moon, 10 grams of water on the earth, 20 grams of ice floating in water on the earth. Put these items in order of increasing weight. And so B is less than A is less than C is the answer. Consider the following. And so these are the same 3 things, but now we're considering mass. And so B is less than C is less than A. That's the correct answer for that one. In terms of density, A is less than C is less than B is the correct answer for that. So an astronaut floats inside an orbiting space station. Which of the following are true? None are true is the answer to this one. So consider the 3 situations below. In each case, 2 small carts are connected by a spring. Constant force F is applied to the leftmost cart in each case. In each situation, the springs are compressed so that the distance between the 2 never change. Which of the following statements must be true regarding the compression of the spring in each case? assume that the springs are identical. The answer is B is less than A is less than C. So consider the three situations below labeled A, B, and C. Ignore friction. After each system is released from rest, how do the tensions in the string compare? The answer is B is less than C is less than A. So two blocks are arranged as shown and kept at rest by holding 1 kilogram, the 1 kilogram block in place. The tension to this string is closest to, the answer is 12 newtons. So two blocks are arranged as shown below and released from rest. The tension in the string is closest to 11 newtons. So a car accelerates down a straight highway. Which of the three body diagrams shown below represents the force in the car? And the answer is number 4. A mass of 5 kilograms sits at rest on an incline, making an angle of 30 degrees to the horizontal. If mu sub s is 0.7, what is the friction force in the block? And the answer is 25 newtons up the incline. Two blocks have the same mass but different sizes. Slide with the same constant speed on a smooth surface. They move onto a surface having friction coefficient mu sub k, which stops in the shorter time. And the answer is both stop at the same time. And then finally, for these questions, two blocks m sub 1, which is greater than m sub 2, have the same speed, move from a frictional surface onto a surface with having a coefficient of friction of mu sub k, which stops in a shorter time. And the answer is both stop at the same time. Okay, we'll just finish up with a summary here. And we've covered an extremely lot of material here, so apologize if this is a little bit dense, but there's 4 forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and the gravitational force. And the forces we're going to be focusing on in this part of our course is the electromagnetic force and the gravitational force. We have the laws of motion. We have Newton's first law, and so which states that an object moving at constant velocity, unless acted on by a force, the tendency for an object to maintain its original state of motion is called inertia. Mass is a physical quantity that measures the resistance of an object to change its velocity. So if an object is at rest, it stays at rest. If it's moving, it stays moving, unless there's external forces. Newton's second law states that an acceleration of an object is directly proportional to the net forces acting on it and inversely proportional to its mass. The net force acting on an object equals the product of its mass and acceleration. So F equals ma. That's a nice equation to thinking about, to keep, to remember. And Newton's universal law of gravitation relates the gravitational forces between two objects, which is illustrated in the figure, and the equation is given here. So for the laws of motion, the weight W of an object is the magnitude of the force of gravity exerted on that object, and is given by W equals mg, where g is the acceleration of gravity. And so this is how we can determine the relationship between mass and weight, and we have to involve gravity. And so Newton's third law states that if two objects interact as shown in the figure, so the force F12 exerted by object 1 and object 2 is equal in magnitude and opposite direction to the force F21 exerted by the object 2 and F1. And so we're showing an example of a hammer. And so these forces are equal. And if this force is greater than the force coming back from the wall, then the nail is going to be driven into the wall. We talked about some different cases. And so here's the normal and kinetic friction forces example. So the normal and kinetic friction forces, and the normal forces is a response of a surface to contact with a given object. There are 4 common physical context for the normal forces. And so the first is that at rest on a level surface, the applied force at an angle. That's the second case that we're showing here. We have a third case as a level surface under acceleration. And then we have a slope surface in case 4 is also useful to know the component of the gravitational force acting down upon a slope. In terms of kinetic friction forces, the magnitude of the kinetic friction force F sub k acting on an object moving on a surface is given by the equation here. And so just a quick summary on those. For static friction force, the magnitude of the static friction force acting on an object at rest satisfies the inequality shown, where n is the normal force and mu sub s is the coefficient of the maximum static friction force between the objects and the surface. Notice that only the maximum static friction force F sub x max involves the use of static friction coefficient mu sub s. In general, the static friction forces is found by solving for the second law of thermal equilibrium. And for the tension forces are conveyed by the use of strings, cords, or cables. Finding their values involves using the second law of equilibrium, and solving for the tensions. And applied force can also create a tension force. Unlike problems involving the normal force, there are numerous contexts. Some examples follow that the object considered a point. And so case 1, we have a vertical tension on a static object. Case 2, a vertical tension forces an accelerating object. Case 3 is 2 tension forces, symmetrical cases where the angles are not equal. It's necessary to develop 2 equations and 2 unknowns using Newton's second law of motion for equilibrium. And for the application of Newton's laws, an object in equilibrium has no external force acting on it, and the second law in component form gives the first line of equations. These 2 equations are useful for solving a problem in statics in which the object is at rest or moving at constant velocity. An object under acceleration requires the same 2 equations with the acceleration terms included. When the acceleration is constant, the equations of kinematics can supplement Newton's second law. And then for a 2-body problem, if 2 bodies are interacting with each other, the second law of motion must be developed for each individual body and simultaneously solve the resulting equations. If the interaction involving 2 objects connected by an inextensible string so that the bodies have a common acceleration, it's possible to use a system approach. The system approach involves not only forces external to the system, not internal forces between the 2 bodies forming the system. Internal forces must be found by applying the second law to individual bodies in the system. Okay, that's a lot of information, but that'll conclude our lecture for now. So thank you very much.